Hello everyone. Let's begin with a quick question. If two triangles both have angles 60, 60 and 60 degrees, are they necessarily congruent? The answer is no. Take one equilateral triangle with side 5 cm and another with side 10 cm. Both have identical angles, but one is much larger than the other. They are similar, not congruent. So, even if all three angles match, called the AA condition, we only get similarity. Congruence requires both size and shape to be identical. Let's dive into a beautiful property of isosceles triangles. Equal sides give rise to equal angles. Suppose we have triangle ABC with side AB equal to side AC. To prove the base angles equal, we draw the angle bisector AD meeting side BC at point D. Now look closely at the two smaller triangles ABD and ACD. In these, side AB equals side AC, angle BAD equals angle CAD because AD is the bisector and side AD is common. By the side-angle side or SAS rule, triangle ABD is congruent to triangle ACD. And if these two are congruent, it directly follows that angle B equals angle C. So we've proven that if two sides of a triangle are equal, then the angles opposite to them are also equal. Quick insight, this neat property comes straight from SAS congruence. It's the key to establishing equality of base angles in isosceles triangles. That's the power of logical reasoning in geometry. Hello everyone. Let's talk about a special shortcut for proving congruence in right-angled triangles, the RHS criterion. Think about this. Whenever you deal with right-angled triangles, measuring angles isn't always easy. But if you already know that the right angle is fixed, then all you really need to compare are the hypotenuse and one other side. This brings us to Theorem 7.5, the RHS rule. It states that if two right-angled triangles have their hypotenuse equal and one side equal, then the triangles are congruent. Notice something important here. The right angle is not the included angle, yet the triangles still become congruent. That's what makes RHS a special case of the side-angle side rule, tailored just for right triangles. As you can see in the figure, both triangles have a hypotenuse of 5 cm and a base of 4 cm. Without even checking the other angle or side, we can confidently say that these two triangles are congruent by RHS. Here's the quick insight. RHS saves time and avoids unnecessary angle measurements. It's like a handy shortcut for right-angled settings. Hello everyone. Let's explore how perpendicular bisectors can be proved using congruence rules. Imagine we have 2 points P and Q, which are equidistant from A and B but on opposite sides of line AB. That means P and Q are kind of like mirror points with respect to AB. Now, look at the two triangles PAQ and PBQ. Here, side AP equals side BP, side AQ equals side BQ, and side PQ is common to both triangles. So, by the side-side-side criterion, the two triangles PAQ and PBQ are congruent. And what does congruence tell us? It tells us that corresponding angles are equal. That means angle APQ equals angle BPQ. This leads us further. If we consider triangles PAC and PBC, then by side-angle side congruence, we conclude that line PQ is perpendicular to line AB and, in fact, bisects line AB. So, with a simple combination of side-side-side and side-angle side, we have proved that line PQ is the perpendicular bisector of line AB. Here's the quick insight. Often, you don't need new theorems for perpendicular bisectors. A clever combination of congruence rules is enough. Hello everyone. Let's take a curious case of equidistant points from two lines that intersect. Suppose lines L and M intersect at point A. Now, we have a point P which is equidistant from both of these lines. That means the perpendicular from P to line L and the perpendicular from P to line M are of equal length. Let's call those perpendiculars PB and PC, and we are told PB equals PC. Now, look carefully at the right-angled triangles APB and APC. In both of them, the hypotenuse AP is common and the legs PB and PC are equal. So, by the right hypotenuse side criterion, triangle APB is congruent to triangle APC. And what does this congruence tell us? It tells us that angle PAB equals angle PAC. In other words, point P must lie on the angle bisector of angle BAC. So here's the quick insight: whenever a point is equidistant from two intersecting lines, it always lies on the angle bisector of the angle between them. A beautiful shortcut that combines geometry and symmetry. Hello everyone. Let's explore how sometimes a single congruence rule isn't enough. We need to combine multiple rules to reach the conclusion. We start with triangle APB, where point P is equidistant from A and B. A line PQ is drawn through P, meeting AB at point C. Our goal is to prove that PQ is perpendicular to AB and that it also bisects AB. First, let's compare triangles APQ and BPQ. Notice that AP equals BP, AQ equals BQ, and side PQ is common. So, by the side rule, triangle APQ is congruent to triangle BPQ. That directly gives us angle APQ equal to angle BPQ by the principle of corresponding parts of congruent triangles. Now let's move forward. Consider triangles APC and BPC. Here again, AP equals BP, side PC is common, and angles APC and BPC are equal from the previous result. So, by the side angle side rule, these two triangles are congruent as well. This means AC equals BC and angle ACP equals angle BCP, which is 90 degrees. So, we have successfully proved that PQ is perpendicular to AB and that it also bisects AB. The quick insight here is that advanced geometry problems often need a chain of congruence rules, not just one, but multiple steps to reach the final proof. Isn't it interesting how layering these rules together gives us a complete picture? Let's bring it all together. Three equal angles, or AA, only give us similarity, not congruence. The SSS rule guarantees congruence when three sides are equal. The RHS rule applies to right-angled triangles with equal hypotenuse and one side. Applications include perpendicular bisectors, angle bisectors, and symmetry in geometry. And remember, once congruence is proved, CPCT, corresponding parts of congruent triangles, lets us unlock even more equalities. So, with SSS and RHS added to our toolkit, our congruence tests are now stronger and more versatile. In the next video, we'll take these congruence ideas further into applications and proofs, making geometry even more exciting.